When you send a message across the world, the interface makes it feel weightless. Tap a screen, and the data disappears into the cloud. You might imagine satellites carrying it above the weather, but for international traffic, the cloud is mostly underwater. More than 99% of international data moves through fiber optic cables laid across the ocean floor. The video call, bank transfer, game update, or business file crossing an ocean usually begins as light inside a strand of glass. That creates a strange contradiction. Modern life depends on a global network that feels invisible, yet much of it runs through physical lines that can be caught by an anchor. A deep ocean cable is not a giant internet pipe packed with websites. At its center are thin optical fibers. Lasers encode information into pulses of light and send those pulses through the glass. Around the fibers are protective layers for strength, insulation, and water resistance. Near shore, where ships, fishing gear, and waves create more risk, a cable can receive heavier steel armor and may be buried beneath the seabed. In deep water, the cable can be much slimmer because fewer human activities reach it. Across a long route, repeaters amplify the optical signal. Landing stations on both coasts provide power, transmission, equipment, monitoring, and connections to terrestrial networks. So, the cable is not one object, it is a machine thousands of kilometers long, with wet equipment below the sea and dry equipment on land. Imagine sending a photo from New York to London. It first travels through local and national networks toward a coastal landing station. From there, traffic is assigned to an available route and converted into optical signals for the ocean crossing. At the far landing station, those signals return to terrestrial fiber and continue toward the destination network. The route may not be the shortest line you could draw on a globe. Engineers must consider water depth, seabed terrain, earthquake zones, fishing grounds, shipping lanes, permits, protected areas, and the locations where a cable can safely come ashore. The internet looks like a cloud because software hides this geography. Underneath, it is a map of ports, trenches, contracts, power systems, and carefully chosen paths across the seabed. Satellites are essential where terrestrial and submarine networks cannot easily reach. They can restore limited connectivity after disasters, connect remote communities, and provide alternative paths, but the international internet needs enormous, continuous capacity. Fiber can carry huge volumes of data along a fixed route, and new cable systems keep adding more capacity. Satellites and cables, therefore, solve different parts of the problem. One offers flexible reach from above. The other carries the bulk of international traffic below. This is why a network that markets itself as wireless still depends on an extraordinary amount of wire. The most common danger is not a spy submarine, it is ordinary work at sea. Fishing gear can snag a cable. An anchor dragged across the seabed can cut or crush one. Dredging and other coastal activity add more risk near shore. Natural hazards matter too. Earthquakes, underwater landslides, volcanic activity, and shifting ice can damage several sections or routes. Components can also fail as systems age. This happens more often than most users realize. The ITU reported more than 200 cable repairs worldwide in 2023, more than 3 every week. A later ITU backgrounder reported more than 170 repairs in 2025, close to 4 per week. Most of those incidents never become global news because a broken cable and a broken internet are not the same thing. Large networks are designed with alternatives. If one cable fails, operators can move traffic onto another undersea cable, a terrestrial route, or, for limited service, a satellite connection. Companies may reserve spare capacity or agree to carry one another's traffic during an outage. That redundancy explains why millions of people can use the internet while a repair ship is already heading toward a fault they never noticed. But redundancy is uneven. Several cables may land in the same coastal area, share nearby terrestrial links, or pass through the same geographic choke point. A region with only one international cable has no equivalent escape route. After the 2022 volcanic eruption near Tonga severed the country's connection to Fiji, full international service took about 5 weeks to restore. Satellite links offered some connectivity, but with limited capacity. Resilience is therefore not the number of lines on a map. It is whether those lines fail independently. The repair begins on land. Engineers send a light pulse down the fiber and measure the reflection to estimate where the fault occurred. A specialized cable ship sails to the area with spare cable, testing equipment, grappling tools, and sometimes remotely operated vehicles. The crew locates the damaged line, raises it from the seabed, cuts away the failed section, joins in replacement cable, tests the connection, and lowers it back into the ocean. Weather, water depth, permits, and the availability of a repair ship can turn this into a long operation. The cable may be thin, but the repair system around it is global. Ships, depots, crews, spare parts, maintenance agreements, and governments that allow the work to proceed. The dramatic part of a cable is the ocean crossing. The strategic part may be the place where it touches land. Landing stations concentrate power equipment, network management, and connections to inland infrastructure. If too many routes enter through the same coast or corridor, a storm, construction accident, or deliberate attack can affect several systems at once. Ownership is changing as well. Large technology companies have become major investors in new submarine capacity that can expand the network. But it also means that decisions about routes, landing points, and available capacity increasingly shape which companies and regions have the fastest, most direct connections. The map of the Internet is also a map of economic power. The Internet is not fragile because one cable can end the digital world. It is fragile where many dependencies quietly converge. One landing station, one coastal corridor, one repair ship, one permit, or one country with no alternative route. And it is resilient for equally physical reasons. Another cable, another landing point. Spare capacity, trained crews, and agreements made before anything breaks. So the next time something disappears into the cloud, imagine what actually carries it. A pulse of light entering a glass fiber, crossing a dark ocean, and arriving through a building on the opposite shore. The cloud is not in the sky. It is a physical system, hidden below the interface.